Our universe might be a single page in an infinite cosmic library. This is the mind-blowing concept of quantum realities, a collection of theories so strange they challenge our most basic understanding of existence. We are about to explore 30 of the most fascinating ideas scientists have proposed, from a reality that constantly splits in two to the possibility that we are living inside a simulation. You will gain a completely new perspective on the nature of reality itself. We will uncover if the universe is a glitchy video game and whether every choice you make spawns a new world. What does it truly mean for something to be real? The universe does not choose. This is the radical heart of the many worlds interpretation, a theory born from the mind of physicist Hugh Everett. He proposed that every single quantum event, no matter how small, forces reality to split. Think of the famous Schrödinger's cat, sealed in a box with a radioactive trigger. Common sense tells us the cat must be either alive or dead when we open the box, but Everett said that is just our limited perspective. In truth, the moment the quantum trigger might or might not fire, the universe divides. In one reality, the cat is perfectly alive, purring in its box. In another, equally real branch of existence, the tragic outcome has occurred. Both events happen, just in different worlds that have now diverged forever. This idea completely removes the need for the strange concept of wave function collapse, where a probability suddenly becomes a single fact. Instead, every possibility is realized. Every single time you faced a choice, from what to eat for breakfast to which career path to follow, a new version of you was spun off into a new timeline. In one universe, you took that job offer in a different city. In another, you never even applied. There is a reality where you are a celebrated artist, and another where you are a deep-sea explorer. The version of you listening right now is just one thread in an infinite, ever-branching tapestry of existence, where everything that can happen does happen somewhere. This is not just a thought experiment about cats, but a profound redefinition of reality itself, suggesting a multiverse so vast that every story is being told. But the many worlds view is far from the only story. For decades, the dominant explanation was something entirely different, a theory that places you, the observer, at the very center of the quantum drama. This is the Copenhagen interpretation, forged by the brilliant minds of Niels Bohr and Werner Heisenberg. In this framework, a particle like an electron does not secretly exist in one place or another before you measure it. Instead, it lives in a ghostly state of superposition, a blur of all possible locations and states at once, described by a mathematical wave of probability. It is only when a conscious observer makes a measurement, when someone or something looks, that this wave function collapses. The particle is forced to pick a single, definite reality from the menu of possibilities. Think of it not as a universe that splits, but as a question that remains unanswered until it is asked. Before you open the box, Schrödinger's cat is not alive in one world and dead in another. It is genuinely both and neither, suspended in a paradoxical state that only resolves into a single, classical outcome the moment you peer inside. Your act of observation is what solidifies reality. This leads directly to Heisenberg's famous uncertainty principle, a fundamental limit on what we can know. It states that you cannot simultaneously pinpoint a particle's exact position and its exact momentum. The more precisely you know where it is, the less you can know about where it is going. This is not a limitation of our machines, but a built-in feature of the universe itself. The very act of measuring one property inevitably disturbs the other, highlighting that reality is not a fixed stage, but something that remains fuzzy and undefined until we interact with it. The philosophical implications are staggering. It suggests that the moon is not really there when nobody is looking, or that the entire universe only snapped into its concrete form when the first conscious being evolved to perceive it. This sharp divide between the fuzzy quantum world and the definite classical world we experience is the core of the Copenhagen view, a stark contrast to the endless, branching realities of many worlds. One theory says everything happens, the other says nothing is real until it is seen. Yet another theory suggests our tangible reality is an astonishingly detailed illusion. The holographic principle proposes that our universe, with all its depth and volume, might be a cosmic hologram, a three-dimensional projection from a flat, two-dimensional surface at the very edge of everything we know. This mind-bending concept did not emerge from pure speculation, but from the intense study of the most mysterious objects in existence, black holes. Physicists exploring black hole thermodynamics discovered something peculiar. They found that the maximum amount of information, or entropy, a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon. It was as if all the data describing every star, planet, and person that ever fell into a black hole was not stored within its vast interior, but was instead painted, like a microscopic pixel art, onto its two-dimensional boundary. This revelation led to a radical leap. If a black hole's entire three-dimensional content is encoded on its two-dimensional surface, could the same be true for our entire universe? Imagine the edge of our observable cosmos not as a distant wall, but as a vast, cold, two-dimensional shell, buzzing with an unimaginable density of information. Every event that happens here, every particle of dust, every flash of light from a supernova, is merely a translation of data stored on that remote surface. We are not solid beings moving through a deep space, but complex projections, like characters in a movie whose entire story is written on the flat surface of the film. This principle completely redefines the nature of space and time, suggesting that what we perceive as a solid, continuous reality is a kind of emergent property, a holographic mirage generated from a simpler, lower-dimensional reality. The depth you see around you, the feeling of space stretching out in all directions, is an incredibly convincing illusion, a cosmic trick of the light on a grand scale. If this is true, then the very fabric of our existence is a kind of code, and we are living inside the projection. This idea of countless branching realities gives rise to one of the most unsettling thought experiments of all, quantum immortality. If the many worlds interpretation is correct, then for any event that could possibly cause your death, there must exist at least one universe where you, against all odds, survive. From your own subjective point of view, you would only ever experience the timelines in which you continue to live. Think of a near miss, a car accident you narrowly avoided. In countless other branches of reality, a different version of you was not so lucky. But the you that is aware, the consciousness listening to this, is always the one that made it through. This logic can be extended to any fatal scenario. A fatal disease, a falling object, even the final heat death of the universe. In at least one reality, a version of you persists, somehow evading the end. This does not mean you would live a charmed life, free from injury or pain. You could experience immense suffering, terrible accidents that leave you incapacitated, but you would never cross the final threshold into death. Your conscious experience would simply continue, skipping like a stone across the surface of reality, always landing on a branch where you are still, technically, alive. This forces a deeply philosophical question. Who is the you that survives? Is it the same continuous consciousness, or are you just a momentary awareness attached to one specific thread in the cosmic tapestry? Each time a branch splits, a new version of your mind is created, one that lives and one that dies. The you that continues feels continuous, but is it truly the same self that existed a moment before the split, or merely a new copy with all the same memories? Quantum immortality does not promise a pleasant eternity, but a potentially endless and solitary existence. as you outlive everyone and everything you ever knew across an infinite number of fading worlds. It asks you to consider your own close calls, those moments of inexplicable luck, and wonder if something far stranger than chance is at work in the fabric of your life. Your own continued consciousness might be a statistical anomaly, but what if the entire stage on which it plays out is also an illusion? The simulation hypothesis proposes that our universe, with all its galaxies, stars, and lives, is not the fundamental level of reality. Instead, it is an artificial construct, a simulation running on a computer of unimaginable power, created by a vastly advanced civilization. Philosopher Nick Bostrom formalized this idea with a stark logical trilemma. He argues that at least one of three propositions must be true. The first is that almost all civilizations like ours go extinct before reaching a post-human stage capable of running such simulations. The second is that any advanced civilization that does emerge has exactly zero interest in creating simulated realities. The third, and most provocative, is that we are almost certainly living in a simulation right now. The reasoning is statistical. If even one civilization survives to create vast ancestor simulations, they would likely create millions or even billions of them. The number of simulated minds would therefore vastly outnumber the one original set of biological minds. If you were a conscious being, the odds are overwhelmingly high that you would find yourself in one of the countless simulations, not in the single, original reality. This is not science fiction, but a serious argument about probability. The universe we perceive could be a digital recreation, its laws of physics not fundamental truths but programmed parameters, much like the rules of a video game engine. Look at the world around you. The speed of light acts as a processing speed limit, a cosmic frame rate. The mysterious Planck length, the smallest possible unit of space, could be the pixel size of reality's resolution, the indivisible point below which the simulation does not render. Quantum weirdness, like a particle being in two places at once until observed, might simply be the program optimizing its resources, only calculating the definite properties of a system when a player is looking. The very fact that our universe appears quantized, broken into discrete packets of energy and space, fits elegantly with the idea of a digital substrate. When you see a glitch in a video game, a texture that fails to load or a character that clips through a wall, you are seeing the underlying code break through. Could strange quantum effects be the cosmic equivalent? Particles teleporting through barriers in quantum tunneling, or being spookily connected across vast distances in entanglement, might be evidence of shortcuts in the code or linked variables in the program. If this is true, then every sunrise, every breath you take, and every star in the night sky is part of an artifact of breathtaking complexity, a reality rendered for a purpose we cannot yet fathom. This idea that reality requires an audience finds its ultimate expression in a theory proposed by physicist John Archibald Wheeler. He called it the participatory anthropic principle, and it turns the relationship between the cosmos and consciousness completely upside down. Wheeler suggested that the universe only comes into a definite state when it is observed by a conscious being. We are not passive inhabitants of a pre-built world, but active participants in its very creation. The universe existed for billions of years before life emerged, a vast, hazy realm of quantum potential. But according to this view, it remained in a state of unresolved possibility, a cosmic question mark, until the first conscious mind evolved to look back and finally answer it. This act of observation is what solidifies history, crystallizing a single timeline out of the fog of what might have been. The implications are staggering because they seem to reach backwards in time. Imagine a particle of light, a photon, emitted from a distant star billions of years ago. It travels through the void, a wave of potential, with countless possible paths through the cosmos. It is only when you, here and now, point a telescope at that star and detect that photon that its entire ancient journey is decided. Your observation in the present moment reaches back across the eons and forces one specific history to become real. Your act of looking gives the universe a past. This is the concept of retrocausality, where the present actively influences the past. Picture a single eye, opening for the first time and gazing back towards the fiery dawn of the Big Bang. In that act of perception, the entire cosmic story snaps into focus from the first instant to the present moment. We are not just discovering the universe, we are bringing it into being simply by being here to see it. This principle suggests a cosmos that dreamed of itself for eons, waiting for the spark of awareness to finally wake up and complete the circle of its own existence. It places an immense responsibility on life, casting us not as accidental tourists, but as essential co-creators of everything we know. But what if every choice, every measurement was an illusion? The theory of superdeterminism presents a cosmos of absolute order. A place where nothing is left to chance and free will is a compelling story we tell ourselves. This controversial idea challenges the very heart of quantum mechanics by proposing there is no true randomness in the universe. Every single event, from the decay of a radioactive atom to the decision of a scientist to run an experiment, was determined from the first moment of the Big Bang. The entire cosmic story, including our own lives, was written into the initial conditions of reality, set in motion like an impossibly complex clockwork. This perspective directly confronts the spooky action at a distance that so troubled Einstein. Quantum entanglement, where two particles instantly influence each other across vast distances, seems to require either faster-than-light communication or a strange, inherent randomness. Superdeterminism offers a third, deeply unsettling option. It suggests that the experimenter''s choice of what to measure is not a free act. The particles and the scientist are part of a single, interconnected system, all following a script laid down at the dawn of time. The correlation between the entangled particles is not due to instant signaling, but because their paths and the choices of the observers were always destined to align perfectly, like characters in a play following the same predetermined narrative. There is no spooky action because there was never a true separation to begin with. Every element of the cosmos is linked in a grand, unbreakable chain of cause and effect. This view erases the quantum probability cloud, replacing it with a reality that is, in principle, perfectly predictable if only you knew its starting state in infinite detail. It resurrects the classical, clockwork universe on a far more profound and interconnected scale. The battle between this rigid determinism and the inherent indeterminacy of quantum theory is one of the most fundamental conflicts in all of science. It forces us to ask whether our deepest convictions about making choices are just a sophisticated illusion, a necessary part of the cosmic program we are destined to perform. While superdeterminism suggests a scripted cosmos, another theory offers a different kind of order, one you can almost see. Pilot wave theory revives the beautiful idea of a tangible, mechanical universe. In this hidden variables interpretation, every single particle has a definite position and a real trajectory at all times, whether anyone is watching or not. There is no ghostly superposition, no collapse into a single state upon measurement. Instead, each particle is like a tiny boat, guided by an invisible wave that fills all of space. This guiding wave is the real quantum object, a field of influence that dictates the possible paths the particle can take. The particle itself is just along for the ride, pushed and pulled by the ripples and contours of its pilot. This restores a comforting determinism to the quantum realm. If you could know the exact position of the particle and the precise shape of its pilot wave, you could, in principle, predict its entire future path with perfect accuracy. The universe is not ruled by chance, but by a hidden, underlying physics we are only beginning to understand. The magic of this theory is perfectly illustrated by the classic double-slit experiment. In the standard view, a single electron fired at a barrier with two slits seems to pass through both at once as a wave of probability, interfering with itself to create a stripy pattern on the detector screen. This is the heart of quantum weirdness, but in the pilot wave picture, the story is far more intuitive. The electron is always a single, localized particle. It goes through one slit, and only one. The pilot wave, however, passes through both slits simultaneously. As the wave ripples out from both openings, it creates an interference pattern on the far side. The particle, surfing this complex wave, is simply guided along the paths of least resistance, inevitably being funneled toward the bright bands of the pattern and steered away from the dark ones. The result is the same stripy interference, but it emerges not from a particle being in two places at once, but from a real, physical interaction between a concrete particle and its guiding field. We do not need to abandon the idea of a solid reality to explain the quantum world. We only need to accept that there is a deeper, invisible ocean of cause and effect beneath the surface of everything we see. This theory paints a picture of a universe that is profoundly real and interconnected, where every motion has a definite reason, hidden just out of sight. Perhaps the universe itself grows tired of possibility. This is the core of objective collapse theories, a family of ideas that offer a starkly different solution to the quantum riddle. They propose that wave function collapse is not a ghostly event triggered by a conscious mind, nor is it an illusion born from branching worlds. Instead, it is a real, physical process, as tangible as radioactive decay, that happens spontaneously to every object in the universe. The most famous of these models is known as GRW, named for its creators Gherardi, Rimini, and Weber. They introduced a simple but profound mechanism. Any particle, from an electron to a quark, has a tiny, random chance at any given moment to spontaneously localize, to suddenly snap out of its spread-out wave of probability and pick a definite position in space. For a single, isolated particle, this event is extraordinarily rare, perhaps happening only once every 100 million years. It would spend almost its entire life in a blurry haze of potential locations. But here is the crucial twist. The probability of this spontaneous collapse increases dramatically with the size and complexity of an object. Think of a single water molecule in the ocean. It can remain in a fuzzy superposition for an age, but a droplet made of trillions upon trillions of those molecules is constantly undergoing these localization events. At every instant, some of its constituent particles are randomly snapping into definite positions. For an object as large and complex as a cat or a human being, the probability becomes so overwhelming that collapse is effectively instantaneous. The superposition is shattered before it can even properly form. This elegantly explains why we never see macroscopic objects in two places at once. A baseball never exists in a state of being both a strike and a foul ball. The countless particles that make up the ball are triggering so many spontaneous collapses that its wave function is perpetually pinned down to a single, classical reality. It solves the measurement problem without ever needing to invoke the mysterious role of a conscious observer. The act of measurement simply involves linking a tiny quantum system, like a single particle, to a large, collapse-prone measuring device. The device's own inevitable localization then drags the particle's state down with it, forcing a definite outcome. This theory builds a concrete bridge between the strange quantum realm and the solid classical world we experience. It suggests a universe with two sets of rules, one for the very small, where probability and potential reign for fleeting moments, and another for the world of tables and chairs, where a constant, quiet reign of spontaneous collapses keeps reality firmly anchored in place. We live our lives in the classical world not because we are conscious, but simply because we are made of far too many particles for quantum weirdness to survive for more than a fleeting instant. These spontaneous collapses keep our everyday world solid, but the rules that govern our reality were not always so fixed. The very laws of physics we take for permanent might be nothing more than local ordinances, unique to our own cosmic neighborhood. This leads us to one of the most expansive theories of all, a concept that ties the quantum world directly to the fate of the entire cosmos. The theory of eternal inflation suggests that the Big Bang was not a one-time event, but an endless, self-replicating process. In the first fleeting moments of existence, a field of energy known as the inflaton field underwent a phase of exponential, faster-than-light expansion. This inflationary period stretched the fabric of space itself, smoothing it out and creating the vast, uniform universe we see today. But here is the profound part. According to this model, this inflation never truly stops everywhere at once. Think of a pot of water coming to a rolling boil. Our entire observable universe is just one bubble that formed in that seething, expanding energy. Outside our bubble, inflation continues at an incredible rate, constantly creating new space. And within that endlessly inflating background, new bubbles are constantly nucleating, popping into existence as separate universes, each with its own Big Bang. This is the inflationary multiverse. Each of these bubble universes could have wildly different properties. When a new bubble forms, the inflaton field settles into a random, stable state. This final value determines the fundamental constants of that universe. In one bubble, the force of gravity might be strong, creating universes that collapse almost instantly into black holes. In another, the weak nuclear force could be too feeble for atoms to ever form. We find ourselves in a bubble where the constants are just right for stars, planets, and life to emerge, a concept we know as the anthropic principle. The sheer scale is beyond human comprehension. We are not just one universe, but one infinitesimal bubble in an infinite, ever-growing froth of cosmic domains. Every possible combination of physical laws is realized somewhere in this vast ensemble. This means there is a bubble where you are reading this script in reverse, and another where time itself flows sideways. The quantum connection is fundamental to this whole picture. Those tiny, random fluctuations we discussed earlier, the same ones that cause spontaneous collapses, were also at work during inflation. Stretched to macroscopic size by the rapid expansion, these quantum jitters became the seeds for all the structure we see in the cosmos. The slight variations in density they created eventually grew, through the force of gravity, into the great cosmic web of galaxies, stars, and planetary systems. Every galaxy, every star, every person owes their existence to a microscopic quantum tremor magnified to a cosmic scale. You are literally made from the amplified whispers of the quantum world, a permanent structure born from a fleeting probability. So when you look up at the night sky, you are not just looking at distant points of light. You are gazing at the fossilized imprint of quantum mechanics, a snapshot of the universe's quantum origin, while all around us, in the unimaginable vastness beyond our vision, an infinite number of other cosmic stories are beginning, each with its own unique set of rules and its own version of reality. The strange transition from quantum possibility to solid reality might be governed by a kind of cosmic survival of the fittest. Quantum Darwinism proposes that the classical world we all agree upon emerges through a process startlingly similar to natural selection. In the buzzing quantum fog, countless potential states exist for any object, but only the most robust, stable states survive the relentless scrutiny of the environment. This is the process of einselection, or environmentally induced superselection. Imagine a single, isolated atom. It can exist in a fragile superposition of many different states, a delicate quantum whisper. But the moment this atom is exposed to the world, it is bombarded by photons of light, air molecules, and the faintest gravitational tugs. This environment constantly measures the system, but it does so in a specific way. The fragile, delicate superpositions are quickly disrupted and destroyed by this interaction. They decohere, vanishing into the background noise. Only the most stable states, the ones that can withstand this constant prying, persist. These resilient states are then copied over and over again into the environment. Think of a stone sitting in a sunlit field. Its exact position is not a secret held in a quantum vault. That information is imprinted onto the countless photons bouncing off its surface, on the air molecules brushing against it, on the dust particles settling around it. Anyone who comes along can access this information simply by looking or touching or listening. They do not need to interact directly with the stone's deepest quantum core. They just read the copies that have been redundantly scattered everywhere. This is why we all agree on the position of the moon. Its quantum information has been broadcast so widely and so completely into the cosmos that it has become an objective fact. You see the moon in one place, I see it in the same place, and a telescope on a distant galaxy would confirm it. The moon's location has been selected. It was chosen by the environment to become a classical reality because its positional state was stable enough to be copied a near infinite number of times. This theory solves the puzzle of why we see a single, definite world instead of a blur of probabilities. The quantum states that win the evolutionary struggle are not the most exotic or strange, but the ones that are simplest and most durable, the states that can best replicate their information into the world around them. Our shared reality, then, is not a fundamental truth, but a consensus built from the most successfully disseminated quantum data. This radical view suggests that the universe does business with itself across time. The transactional interpretation proposed by physicist John Cramer presents quantum events not as random collapses, but as settled deals. In this model, every particle emission sends out an offer wave rippling forward through time, exploring all possible paths to a potential detector. But this is only half the story. The future detector, in turn, sends a confirmation wave backward through time, a kind of echo responding to the initial offer. A realized event, like a particle appearing on a screen, only occurs when these two waves, one from the past and one from the future, meet and reinforce each other in a resonant handshake. This transaction across time is what solidifies a single outcome from the quantum haze of possibilities. It is as if reality is a conversation between the past and the future, with the present moment being the point where an agreement is finally reached. This framework provides an astonishingly elegant solution to the puzzle of the double-slit experiment. When you fire a particle at the two slits, its offer wave travels forward and passes through both openings. The confirmation wave from the screen at the back travels backward through time, also passing through both slits. The only places where these forward and backward waves can perfectly line up and amplify each other are along the specific, stripy bands of the interference pattern. A strong transaction forms there, and that is exactly where the particle manifests. The particle does not take a mysterious path. It is simply the visible signature of a completed temporal agreement. This interpretation paints a universe that is profoundly time-symmetric, where the future is just as involved in shaping events as the past. The arrow of time we experience so strongly in our daily lives is merely a statistical trend in a cosmos where the fundamental laws see no real difference between forward and backward. Every click of a Geiger counter, every photon striking your retina, is the result of a delicate negotiation between what was and what will be, a cosmic handshake that writes history in the very moment it is perceived. Our quest to understand reality's fabric now leads us to a theory that reimagines the very stage upon which the cosmic drama unfolds. Loop quantum gravity proposes that space itself is not a smooth, continuous backdrop, but is woven from a tapestry of tiny, finite loops. Picture the universe as a vast, cosmic chainmail suit, with each interlinking ring representing a minuscule, indivisible unit of space. These loops form a vibrating, dynamic network known as a spin foam, a structure that buzzes with quantum activity at the smallest possible scale. This pixelation of reality provides a profound solution to one of physics' greatest puzzles, the terrifying singularity. In Einstein's general relativity, The centers of black holes and the starting point of the Big Bang are described as points of infinite density, where the laws of physics simply break down. But if space is quantized, if it is made of these finite loops, then it cannot be squeezed into an infinitely small point. There is a smallest possible size, a cosmic pixel. This means the gravitational collapse of a dying universe or a star forming a black hole would reach a point of maximum density and then rebound. This leads to one of the theory's most breathtaking predictions. Our universe may not have begun with a single explosive bang from nothing, but with a great bounce. Before our cosmic epoch, there may have been a previous universe that contracted under its own gravity, reached this quantum Chinese letter of density, and then bounced outward, giving birth to the expanding reality we inhabit today. We could be living in just one cycle of an endless cosmic heartbeat, a perpetual rhythm of contraction and expansion stretching across eternity. The very fabric of your being, the space between your hands, and the vast distances between galaxies are all manifestations of this intricate, quantized spin foam, a fundamental grid that underpins everything. Our journey through the quantum tapestry now takes us to one of the most ambitious theories ever conceived, a framework that seeks to unite all of reality under a single, elegant idea. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but unimaginably small, vibrating loops of energy. Think of a tiny, one-dimensional string, so small that if an atom were the size of our solar system, the string would be no larger than a tree on Earth. The magic lies in how these strings vibrate. Just as a single violin string can produce different notes depending on how it is plucked, a fundamental string can vibrate in an infinite number of distinct patterns. One specific resonance might correspond to an electron, while a slightly different vibration creates a quark, and another pattern manifests as a photon of light. In this vision, every particle and every force in nature is simply a different melody played on the same cosmic instrument. This beautiful symphony, however, requires a much larger stage than we are used to. For the mathematics of string theory to work, space cannot have only the three dimensions we experience. The equations demand extra dimensions of space, curled up and hidden at every point in our familiar universe. Imagine a garden hose viewed from a great distance. It looks like a simple one-dimensional line, but if you could shrink down to an ant crawling on its surface, you would discover the second dimension, curled tightly around the hose's circumference. String theory suggests that 6 or 7 such tiny, compact dimensions are woven into the very fabric of our reality, far too small for us to perceive directly. This leads to an even more profound implication, the concept of the string landscape. The way these extra dimensions are folded and twisted determines the properties of our universe, like the strength of gravity or the mass of an electron. But the mathematics reveals not one, but a staggering number of possible stable configurations, perhaps 10 to the power of 500. Each configuration represents a different universe with its own unique set of physical laws. Our universe, with its perfect balance for life, is just one tiny, hospitable patch in a vast, almost infinite cosmic landscape of possibilities. This is a multiverse born not from branching worlds, but from the geometry of hidden dimensions. Yet for all its grandeur, string theory remains one of the most controversial ideas in physics. Its primary challenge is a complete lack of experimental evidence. The energy levels required to see these strings or probe the extra dimensions are far beyond anything our particle colliders can achieve. For now, it exists as a magnificent and mathematically compelling castle in the air, a grand vision of quantum reality that promises ultimate unification, but remains frustratingly out of reach. Even the most voracious cosmic objects cannot escape a fundamental law. Information, in the quantum sense, can never be truly destroyed. It can be scrambled, hidden, or transformed, but its essential imprint must persist. This is the bedrock principle that black holes seem to shatter, creating the most vexing problem in theoretical physics: the black hole information paradox. The crisis began with Stephen Hawking's revolutionary discovery that black holes are not entirely black. Through a subtle quantum process at the very edge of their event horizons, they slowly leak radiation. This Hawking radiation is incredibly faint, but it carries energy away from the black hole, causing it to gradually lose mass and shrink over eons until it presumably vanishes in a final puff of energy. Here lies the terrible paradox. The Hawking radiation itself appears to be completely random, pure thermal noise that carries no data about what fell in. If a star, a planet, or an entire encyclopedia were to cross the event horizon, all the specific information about their structure and composition would be seemingly erased from the universe when the black hole finally evaporates. This violates the sacred rule of quantum mechanics, unitarity, which demands that information must be preserved. It is the cosmic equivalent of burning a library and having not even the ashes remain. The universe would have no memory of what was lost, a fundamental amnesia that physicists simply cannot accept. So where does the information go? One compelling answer brings us back to the holographic principle. Perhaps the information is never actually lost inside the black hole because it was never truly there to begin with. Just as a hologram encodes a three-dimensional image on a two-dimensional surface, all the data describing every object that falls in is meticulously preserved on the event horizon itself, painted onto its surface in unimaginably tiny pixels. The black hole's interior, with its crushing singularity, is an illusion. The real universe, with its complete record of history, is played out on the boundary. When the black hole evaporates, this information is not destroyed. It is somehow encoded into the Hawking radiation, imprinted in incredibly subtle correlations between the escaping particles. The radiation only seems random if you look at each particle individually. But if you could see the entire, intricate pattern across the black hole's entire lifetime, the story of everything it ever consumed would be revealed. Another, more violent solution is the firewall hypothesis. This idea suggests that the event horizon is not the smooth gateway described by Einstein. Instead, it is a searing wall of energy, a literal firewall that instantly incinerates anything that touches it. This would solve the information problem by ensuring that information is never actually lost inside the black hole, because it is violently transformed into energy at the surface. But this comes at a great cost, fundamentally breaking Einstein's principle of equivalence, which states that an astronaut falling through the event horizon should feel nothing special, no dramatic transition. The firewall creates a paradoxical boundary where the laws of physics as we know them simply break down. This paradox is not just an academic puzzle. It is a direct clash between the two pillars of modern physics, general relativity and quantum mechanics, and its resolution will force us to rewrite our understanding of reality. It asks a deceptively simple question with earth-shaking implications. Is the universe a reliable record keeper, or does it allow for the permanent deletion of the past? The answer will determine whether our cosmos is fundamentally logical, or if true, irreversible oblivion is possible. This bizarre connection between information and black holes leads us to an even more profound link, one that ties the weirdest phenomenon in quantum physics directly to the fabric of space and time. The ER equals EPR conjecture proposes a stunning equivalence. It suggests that two entangled particles, linked by the spooky action of quantum mechanics, are actually connected by a microscopic wormhole, an Einstein-Rosen bridge. The EPR part, named for Einstein, Podolsky, and Rosen, represents the paradox of entanglement. The ER part, for Einstein and Rosen, describes a bridge through spacetime. This idea boldly claims they are one and the same thing. Imagine two electrons created together, forever entangled so that measuring one instantly influences the other. no matter the distance. According to this conjecture, they are not communicating faster than light. Instead, a tiny, invisible tunnel stitches space itself together between them. They are not far apart at all. They are neighbors across a hidden fold in reality. This transforms entanglement from a ghostly correlation into a tangible, geometric structure. Spooky action at a distance becomes a simple shortcut through the basement of the universe. The implications are revolutionary, suggesting that the very connectivity of space, the fact that you can move from your chair to the door, emerges from a vast, cosmic web of quantum entanglement. Space is not the primary stage, it is the final product. Think of the universe as a piece of fabric. Each thread in that fabric is a connection of entanglement between 2 points. Weave enough of these threads together, and you create the continuous, smooth sheet of space we navigate every day. If you could somehow cut all the quantum entanglement linking one region of space to another, the fabric of spacetime itself would fall apart. It would dissolve into a disconnected, meaningless foam. This means the chair you are sitting on is physically connected to the most distant galaxy, not by empty space, but by an immeasurably complex network of these tiny, invisible bridges. Every object is held in place by a silent symphony of quantum links. The universe is not just filled with entanglement, it is built from it. But what if the quantum world's strangeness is not a puzzle to be solved, but a reflection of our own personal perspective? Quantum Bayesianism, or cubism, offers this startlingly intimate view. It proposes that the probabilities at the heart of quantum mechanics are not objective features of the universe. They are not ticking clocks hidden inside atoms waiting to be discovered. Instead, they are personal degrees of belief, much like the confidence you might have in a weather forecast. A quantum state is not a picture of a particle itself, but a user manual for you, the agent, interacting with the world. It encapsulates your expectations, your best guesses for what will happen when you reach out and perform a specific experiment. This framework dissolves many of the old paradoxes with a simple shift in viewpoint. Take Schrödinger's cat. In cubism, asking if the cat is alive or dead before you look is a meaningless question. The quantum probability is not a statement about the cat's true state, but a tool in your own mind, a representation of your uncertainty about what you will find when you open the box. Your observation is not a magical act that collapses a wave. It is simply you updating your own internal manual based on new, direct experience. The universe does not lurch between states, you do. This is a radical departure from the quest for a single, objective reality. Cubism is not about what the world is, but about how we navigate it. It places you, the conscious user of quantum theory, at the very center of the story. The mathematics works not because it describes a hidden clockwork, but because it is an exceptionally powerful guide for making bets about your future sensory experiences. This makes every quantum measurement a personal event. When you measure an electron's spin, the result is not a revelation of a pre-existing fact. It is an outcome created in the interaction between you and the electron, an outcome that becomes a new piece of your own unique history, which you will then use to inform your next set of expectations. So where does that leave reality? For a cubist, reality is the complex tapestry of these personal experiences and interactions. There is a world out there, of course, but we can only ever know it through the lens of our own agency, through the bets we make and the outcomes we record. This theory asks you to consider your own role not as a passive observer of a predetermined cosmos, but as an active participant who is constantly shaping and being shaped by your own quantum reality. Every choice you make, every measurement you take, is part of your ongoing, personal conversation with existence. Our own present moment might be a two-way street in time. Time-symmetric quantum mechanics proposes that the flow of time is not a one-way river from past to future, but a structure with perfect symmetry. In this radical view, the fundamental laws of physics work just as well backwards as they do forwards, and influences can travel in both directions. This idea was powerfully captured by the Wheeler-Feynman absorber theory. They asked a simple but profound question about a single electron. When an electron jiggles, it emits radiation, ripples of energy that fly outward. But why? What tells the electron to radiate? Their answer was as elegant as it was strange. The electron radiates because the entire future universe is there to absorb the waves. The absorption of the energy in the far future sends a confirmation signal backward through time, a wave traveling from tomorrow to yesterday, that encourages the electron to emit the radiation in the first place. The action of the future is required to explain the events of the present. This is retrocausality in its purest form, where a future event is a genuine cause of a past event. This shatters our everyday, linear perception of cause and effect. We think of a row of dominoes where the fall of the first causes the fall of the second. But what if the fall of the final domino somehow reached back and helped push the first one over? Imagine a cosmic artist who begins a painting. In our normal view, each brushstroke is a cause that creates the final effect, the finished masterpiece. But in a time-symmetric universe, the artist is also guided by the completed painting that exists in the future. Its perfect composition reaching back to influence where each stroke is placed in the past. The final form is actively participating in its own creation. This provides a startlingly intuitive explanation for some of quantum mechanics' deepest puzzles, like the double-slit experiment. A particle's path seems to be influenced by where it will end up. The interference pattern emerges because the particle is not just moving from the source to the screen. It is also responding to the detector in its future, engaging in a kind of handshake across time that defines its journey. This forces us to confront a dizzying possibility. The universe might not be unfolding from a single starting point, but is instead a single, timeless whole. A four-dimensional block where every moment, from the Big Bang to the last star's death, exists eternally. Our conscious experience of a flowing present is just a local illusion, a cursor moving along a cosmic DVD where all the scenes already exist. Your choices feel free, but could they also be subtly shaped by the person you are destined to become? The solid stage of space and time you stand on might be a grand illusion, a collective mirage born from something far more fundamental. Emergent spacetime theory proposes that our four-dimensional continuum is not a primary ingredient of the universe, but a secondary effect, a consequence of deeper quantum processes. We are so accustomed to moving through space and marking time that it feels like the bedrock of reality. But this theory suggests it is more like the surface of a lake, a smooth appearance that hides a chaotic, swirling world beneath. Think about the concept of temperature. You can feel that a cup of coffee is hot without knowing a single thing about atoms. The heat is a real, measurable property to you. Yet, at its root, temperature is not a fundamental entity, it is an emergent property. It arises from the average kinetic energy, the frantic jiggling, of trillions of molecules. The heat emerges from the collective behavior of things that are not, themselves, hot. Emergent spacetime theory applies this same logic to the fabric of the cosmos. The smooth geometry of spacetime described by Einstein, the curvature that guides planets and traps light, may not be the final word. It could be a large-scale approximation, a kind of average, that emerges from a vast network of quantum information or a seething foam of entanglement. We do not need to know about this underlying quantum substrate to navigate our world, just as we do not need to know about atoms to use a thermometer. But for physics, this shift in perspective is revolutionary. It offers a potential path to resolve the century-old conflict between general relativity and quantum mechanics. The problem has always been that gravity, described as the curvature of smooth spacetime, refuses to play nicely with the fuzzy, probabilistic rules of the quantum world. But if spacetime itself is not fundamental, then the conflict vanishes. It is like two people arguing over the properties of a rainbow. One is describing its beautiful, continuous arc of color, while the other is insisting it is made of countless, individual droplets of water. They are both describing the same phenomenon, just at different levels of reality. In this new picture, general relativity describes the smooth, emergent rainbow, while quantum mechanics describes the underlying droplets, the fundamental quantum constituents from which spacetime condenses. This could mean that at the tiniest possible scales, the Planck scale, the very concepts of here and there, before and after, lose their meaning. Reality becomes a relational network, a web of quantum connections where notions of distance and duration are not givens, but are derived from the strength of the links between nodes. Visualize a digital photograph on your screen. From a distance, it appears as a seamless image with smooth gradients and curves. But if you zoom in incredibly close, you see the truth, a grid of discrete, individual pixels, each one a block of pure color. The emergent spacetime view suggests our universe is like that picture. The smooth, continuous reality we experience is the image, while the pixelated grid, the true fundamental level, is a dynamic quantum network. The passage of time itself might emerge from the way the connections in this network change, creating the illusion of a flowing present from what is essentially a vast, timeless structure. This theory invites us to consider that the stage of the universe is not a given, but a performance, an appearance that emerges from the silent, intricate dance of countless quantum players. The very fabric of your conscious experience, that inner world of thoughts and sensations, might be rooted in the smallest structures of the universe. This is the daring proposal of orchestrated objective reduction, or OR, a theory forged by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They ask a question that most physicists avoid. What if consciousness is not simply a computation running on the wetware of the brain, but a genuine quantum phenomenon? Their answer lies deep within your brain cells, in structures called microtubules. These are intricate, cylindrical scaffolds that form the skeleton of neurons, and Penrose and Hameroff propose they are the quantum computers of the mind. Within these tiny tubes, electrons can become entangled, existing in a delicate superposition of states, a quantum symphony of possibilities. This is where gravity enters the picture. Penrose argued that a superposition becomes unstable when the mass-energy difference between the possible states reaches a certain threshold. The very curvature of spacetime, dictated by gravity, can no longer tolerate the ambiguity. It forces a collapse. In the brain, this collapse is not random. It is orchestrated by the biological structure of the microtubules, which guide the quantum process toward a specific, meaningful outcome. And here is the most profound part. Each of these orchestrated collapses is not just a neural event. According to the theory, it is a discrete moment of conscious awareness. Your stream of thought is not a smooth flow, but a series of these tiny quantum ripples, each collapse selecting a definite state from a cloud of potential, giving you a single, coherent thought or sensation. This provides a potential bridge across the deepest chasm in science, linking the objective world of physics with the subjective world of mind. It suggests that you are not just observing quantum reality from the outside. Your consciousness is an active participant, a process born from the same quantum gravitational physics that governs the cosmos. This idea has been met with fierce criticism. Many scientists argue the warm, wet, chaotic environment of the brain would destroy any fragile quantum coherence almost instantly, far too quickly to play any role in our fast-paced thoughts. Yet the theory persists, a bold challenge to our understanding of ourselves. It implies that your mind is not a mere bystander in a clockwork universe. It is an integral part of the quantum dance, a process where the cosmos, through the structure of your brain, becomes aware of itself. Black hole complementarity offers a startling escape from the information paradox, proposing that reality itself depends on who is asking. This principle asserts that two seemingly contradictory stories can be simultaneously true. From the perspective of an astronaut falling freely toward a black hole, the event horizon is not a dramatic barrier. It is a smooth, uneventful gateway, and the astronaut passes through it without incident, their information traveling intact toward the mysterious singularity at the core. But for a distant observer watching from a safe distance, a completely different reality unfolds. They would see the astronaut's image slow down, redden, and appear to freeze just at the edge of the horizon, their forms smeared into a faint, hot imprint on the surface. According to this outside view, the astronaut never actually enters the black hole. Instead, all their information is scrambled and reflected back out, encoded into the Hawking radiation slowly leaking from the surface. So which story is correct? Is the information destroyed inside or preserved outside? Complementarity declares that both are valid within their own frames of reference, and that there is no single, God's eye view that can reconcile them. It is a radical form of relativity where the universe forbids any one observer from seeing the contradiction firsthand. The falling astronaut sees one truth, the distant observer sees another, and neither can communicate their version to the other to prove it. This is where the hologram analogy becomes so powerful. Think of the event horizon as a vast, spherical film. When an object falls in, it does not simply vanish. From the outside perspective, its information is instantly photocopied onto this shimmering, two-dimensional surface, much like a three-dimensional image is encoded on a flat piece of holographic film. The original may appear to pass through, but a perfect copy remains, preserving the data for the external universe. The laws of physics are saved from paradox because information is never duplicated in a single frame of reference. For the falling astronaut, their information crosses the horizon. For the outside observer, it is painted onto the horizon. No one ever sees two copies being made. This solution profoundly challenges our instinct that there is one objective reality everyone must agree on. It suggests that the cosmos is built to accommodate multiple, incompatible truths, and that the preservation of fundamental law is more important than our classical notion of a single, consistent narrative. What we call reality may just be a matter of perspective, a story that changes depending on where you are standing in the universe. Some realities are built on a foundation of time itself. Causal set theory offers a breathtakingly minimalist vision, proposing that the true fabric of existence is not a smooth, flowing continuum, but a vast collection of discrete events, like individual grains of cosmic sand. This immense collection is known as a causal set, a sprawling network where each point is a fundamental event, and the connections between them represent the only truly fundamental relationship in the universe, cause and effect. One event can either influence another or it cannot. There is no fixed distance or duration here, only this raw, partial ordering of what leads to what. The beautiful, curved spacetime described by Einstein, with its gravitational wells and cosmic expanses, is not the starting point. It is an emergent illusion, a large-scale approximation that condenses from this underlying web of causality. Think of a classic black and white film. When you watch it, you see fluid, continuous motion, a seamless story unfolding. But if you examine the film strip itself, you find it is just a sequence of static, individual frames. The smooth motion is an artifact of your perception, emerging from the rapid succession of these discrete images. In the same way, our continuous experience of space and time emerges from the intricate, causal connections between the universe's fundamental events. The feeling of a moment flowing into the next is a consequence of this deep, causal structure. This approach naturally explains one of the great mysteries of our experience, the arrow of time. In most physical laws, time is symmetric, but we only ever remember the past and anticipate the future. In a causal set, this directionality is built in from the very beginning. The network has an inherent growth, a fundamental unfolding from one event to its effects, providing a concrete origin for time's relentless forward march. This elegant framework also sidesteps one of the most troubling aspects of general relativity, the singularity. The terrifying points of infinite density at the heart of black holes and the beginning of the Big Bang are, in this view, simply artifacts of trying to describe a discrete, grainy reality with a continuous model. It is like trying to describe the precise, pixelated edge of a digital photograph using only the language of smooth curves. You will inevitably get nonsense. In causal set theory, there is a finite number of fundamental events, so density can never become truly infinite. The theory suggests that what we call a singularity might just be a region of incredibly dense, but ultimately finite, causal connection. It replaces a mathematical paradox with a physical, albeit strange, reality. This is a universe where connection is more fundamental than location, and where the entire cosmic story is written in the silent, irreversible language of cause and effect. The origin of space itself may be a story of cosmic freezing. Quantum gravity is a theory that proposes our three-dimensional world was not always here. It emerged from a state of pure connection, a time before here and there even had meaning. In this model, the fundamental ingredients of reality are not particles or waves, but simple quantum bits of information. In the universe's first searing moments at energies beyond comprehension, these bits existed in a state of complete connectivity. Picture a vast, buzzing network where every single point is directly linked to every other point. This is a complete graph, a cosmic fire where the concept of distance is meaningless because everything is, in a sense, right next to everything else. There is no space, only relationship. Then, as the newborn universe expanded and cooled, a profound phase transition occurred, a kind of cosmic freezing. The endless, frantic connections began to stabilize. Most of the links between the quantum bits were severed, turning off like lights across a vast grid. The remaining connections, the ones that survived this great freezing, locked into a rigid, orderly pattern. This frozen network of persistent links is what we now perceive as the three-dimensional space of our everyday reality. The distance between your hand and your coffee cup is not a fundamental void. It is a measure of how many of these frozen connections, these surviving graph links, you must traverse to get from one point to the other. This process of space emerging from a network is called geometrogenesis, the birth of geometry. You can visualize it as a shimmering, hyper-connected web of light, buzzing with infinite possibility. Then, as the temperature drops, the web begins to crystallize. The chaotic light show settles into a stable, lattice-like structure, a cosmic ice forming from the quantum fire. This is the moment space is born, solidifying from a realm of pure connection into the familiar stage we navigate today. This theory provides a stunningly elegant origin story for the very fabric of existence, suggesting that the emptiness around us is not empty at all, but a fossilized remnant of the universe's hottest, most connected state. Yet even if time is an emergent illusion, the observer at its center remains a profound enigma. The many minds interpretation takes the cosmic branching of reality and turns it inward, proposing that the universe does not split, but your own consciousness does. This is a radical twist on the many worlds view, one that places the entire burden of the multiverse squarely within the mind of every observer. When faced with a quantum event, like the fate of Schrödinger's cat, the physical world itself remains whole and singular. The box, the cat, the radioactive atom, they all continue on one path. What splits is not the cosmos, but your awareness of it. At the moment of observation, your single stream of thought fractures into multiple, separate streams of consciousness. One mind perceives a living cat, while another, equally real mind, perceives a dead one. Both of these mental states are real, but they become completely disconnected from one another, forever unaware of each other's existence. This directly tackles a deep issue in the original many worlds theory, the preferred basis problem. If the universe is constantly branching, What defines the specific way it splits? Why do we end up with a world where the cat is definitively alive or dead, and not in some strange mixture of both? The many minds answer is elegant and unsettling. The basis is defined by the mind itself. It is the structure of your consciousness that determines how reality appears to you, selecting one definite outcome from the quantum soup. You are not a passive traveler on a single branch of a giant cosmic tree. You are the tree, perpetually branching inward with every quantum decision you witness. This makes the theory intensely personal. Every time you check the weather, glance at a traffic light, or even observe the spin of an electron, your mind is silently dividing. There is a version of your awareness that sees rain, and another that sees sunshine. One sees a green light, and another a red. Each of these mental threads believes it is the only one, convinced of its solitary reality, never knowing that countless other versions of its own thoughts are unfolding in parallel. The universe remains a single, objective entity, but it is viewed through the infinite, fractured lens of conscious perception. This transforms the quantum mystery from a question of physics into a question of identity. It asks you to look within and wonder if the you listening right now is just one thread of awareness in a vast, silent tapestry of minds, all sharing the same origin but forever isolated, each one living in its own private version of a shared world. This emptiness surrounding us may not be empty at all, but a fluid of perfect stillness. The superfluid vacuum theory reimagines the void of space as a cosmic ocean, an unimaginably cold and thin superfluid that extends throughout the entire universe. A superfluid is a state of matter with zero viscosity, meaning it flows without any friction whatsoever. In this model, the vacuum of space is not a passive stage but an active, physical substance. The particles that make up everything you see, from the screen in front of you to the stars in the sky, are not tiny, solid balls. Instead, they are excitations in this superfluid, like whirlpools or ripples on its surface. An electron is not a point, but a stable, swirling vortex in the fluid. A photon of light is a wave traveling through it. In this view, the entire zoo of subatomic particles are simply different kinds of vibrations and knots in the fabric of this fundamental medium. This elegant idea has a profound consequence. It can naturally replicate the rules of both Einstein's relativity and quantum mechanics. The speed of light becomes the natural speed of sound waves in this superfluid. The reason nothing can go faster than light is for the same reason nothing can travel faster than sound in air. It would break the fundamental properties of the medium. The strange quantum behavior of particles, like being in two places at once, can be understood as the fluid itself exploring all possible paths before settling into a coherent ripple. This perspective offers a potential solution to the greatest mysteries of modern cosmology: dark matter and dark energy. Dark matter, the invisible mass that holds galaxies together, might not be a cloud of unknown particles. It could be a subtle pressure effect, a kind of background current within the superfluid vacuum that exerts a gravitational pull. Dark energy, the force driving the universe's accelerated expansion, might be an intrinsic property of the superfluid itself, a kind of internal tension or negative pressure that causes the entire medium to stretch. Imagine the cosmos as a vast, still pond. The galaxies are like intricate whirlpools on its surface. The invisible tug we call dark matter could be the gentle pull of the waters circulating around those whirlpools. The force of dark energy would be the pond itself slowly, inexorably expanding, stretching its own surface and carrying the whirlpools along with it. We are not separate from this fluid, we are patterns within it, temporary structures in an eternal, flowing medium, all of us riding the gentle currents of a superfluid sea. The universe could be a cosmic computer game, running on a grid of unimaginable scale. This is the compelling idea behind the cellular automaton universe. Picture an infinite chessboard where every single square or cell follows a tiny set of simple rules. The state of each cell, whether it is on or off, alive or dead, is determined solely by the states of its immediate neighbors. There is no grand plan, no central controller, just local interactions. Yet, from this stark simplicity, breathtaking complexity can emerge. You can see this for yourself in Conway's Game of Life, a digital petri dish where patterns of cells are born, evolve, and die according to just a few fundamental laws. Gliders can sail across the grid, spaceships can be constructed, and entire computational circuits can be built, all without any programmer guiding their path. The intricate dance arises spontaneously from the bottom up. Now, magnify that simple grid to the scale of the cosmos. Imagine that the very fabric of spacetime is a lattice of discrete points, each one a fundamental cell. The particles we think of as electrons and quarks are not tiny balls, but stable, moving patterns on this grid, like gliders on a cosmic scale. The forces we experience, like gravity and electromagnetism, are not fundamental fields, but the emergent consequences of the local rules governing how these patterns interact with one another. What we perceive as the smooth, continuous flow of time is merely the sequential updating of the entire cosmic grid, one tick of the clock after another. The illusion of a fluid reality is just our limited perspective on a universe that is, at its heart, digital and discrete. This view presents a universe of absolute determinism. If you knew the exact state of every cell and the rules they follow, you could, in principle, calculate the entire future of the cosmos. There is no true randomness, only the majestic, unfolding consequence of the initial configuration. This forces a difficult question about our own lives. If the universe is a deterministic computation, is our sense of free will just another sophisticated pattern? A compelling story generated by the cellular automaton to explain its own internal states. We feel like we are making choices, but are we simply watching a movie of ourselves that was rendered at the beginning of time? The theory does not necessarily deny our experience, but reframes it. Your thoughts and decisions are real patterns within the computation, but they are patterns that were always destined to unfold according to the code. This leads directly back to the haunting possibility of a simulated reality. If our universe can be so accurately described as a computational system, it becomes far more plausible that it actually is one. We could be living inside a simulation running on some unfathomable computer in a higher reality. A thought that transforms the night sky into a display of stunning resolution and our lives into narratives of profound, if programmed, meaning. Our classical logic, with its rigid true or false binary, struggles to capture the fluid essence of the quantum domain. Nutrisophic logic offers a third path, a powerful new language that embraces the inherent uncertainty of reality itself. Developed by Florentin Smerandake, this framework introduces a crucial third value, an indeterminate or neutral state that exists alongside true and false. It is not simply a maybe, but a formal recognition of the overlapping, partial truths that define the quantum world. This directly mirrors the heart of quantum superposition, where a particle genuinely exists in a state that is neither definitively here nor definitively there, but a complex fusion of both possibilities. Nutrisophic logic provides the mathematical grammar to describe this blurry existence without forcing it to prematurely collapse into a single, classical fact. It allows us to say a particle is 70% here and 30% there, or that it occupies a state that is both true and false to varying degrees, a concept our everyday logic simply cannot process. This approach has the potential to untangle some of the most stubborn quantum paradoxes. Take Schrödinger's cat once more. In a nutrisophic view, the cat is not a confusing mix of alive and dead, a statement that breaks classical logic. It exists in a nutrisophic state where the values of alive, dead, and indeterminate coexist and interact. The paradox melts away when our logic itself is expanded to formally include the indeterminate as a valid, fundamental component of reality. The universe is not failing to give us a straight answer. We have simply been asking the question with an outdated vocabulary. By weaving indeterminacy directly into the fabric of logic, we build a tool that might finally map the true, fuzzy terrain of the quantum realm, suggesting that reality operates on a spectrum of truth that our binary minds are only beginning to decode. Another hidden world could be brushing against our own, a universe built from mirror matter. This is not a parallel reality branching from our choices, but a complete cosmic duplicate, a shadow realm woven into the very fabric of our existence. The theory suggests that for every particle we know, from the quarks in your hand to the photons from the sun, there exists an identical twin, a mirror particle. These shadow particles would form their own atoms, governed by their own version of the fundamental forces, creating mirror planets, mirror stars, and perhaps even mirror life. The only bridge between our world and theirs is the weakest and most pervasive force of all, gravity. This single, ghostly connection could be the answer to one of astronomy's greatest puzzles, the mystery of dark matter. We see the gravitational effects of this invisible mass holding galaxies together, but our telescopes see nothing. If dark matter is simply the collective gravity of an entire mirror universe overlapping our own, it would explain why it is everywhere, yet completely undetectable to our instruments. Our light simply passes through their world, and theirs through ours, leaving only the gentle tug of gravity as evidence of their presence. Picture our galaxy, the Milky Way, not as a solitary island of stars, but as a cosmic double exposure. A brilliant, swirling disk of our familiar stars and gas, and superimposed upon it, a second, fainter galaxy made entirely of mirror matter. The two pass through each other like ghosts, feeling each other's weight but never colliding, never interacting in any way except through that silent, mutual gravitational pull. This means there could be a mirror Earth occupying the exact same space as our own, a world with mirror mountains and mirror oceans, its inhabitants forever unaware of our bustling reality just a breath away. The profound isolation between our worlds raises a haunting question. If mirror life exists, what form would it take? Would its history mirror our own, or would it have spun a completely different story from the same cosmic laws? We may never know, for we are prisoners of our own light, our own forces, forever sensing the presence of a neighbor we can never truly meet. Your own persistent gaze could stop time for a quantum particle. This is the strange magic of the quantum Zeno effect, a phenomenon where reality can be frozen solid by the simple act of watching it. Named after the ancient Greek philosopher Zeno, who argued that a flying arrow must be motionless at every single instant, this effect reveals that constant observation can prevent change from ever occurring. The classic example involves an unstable radioactive atom poised to decay. Left unobserved, it will eventually spit out a particle and transform. But if you rapidly and repeatedly measure it, checking its state over and over again, something incredible happens. The atom is caught in its initial state, like a deer in the headlights of your attention, and it never decays. Your measurement resets its internal quantum clock, forcing it to remain in its unstable condition indefinitely. This is not a mere theoretical trick. It has been demonstrated in laboratory experiments with atoms and particles. The act of looking, of interacting with the system to ask the same question again and again, actively holds reality in place. This raises a profound philosophical puzzle. Does this require a conscious mind to do the observing, or is any physical interaction enough? Most physicists lean toward the latter, that any interaction that extracts information from the system, whether by a human, a machine, or even a stray photon of light, can trigger the freeze. The universe does not care about consciousness, only about the disruptive exchange of information. Yet, the implications are no less staggering for our own experience. It suggests that our focused attention on the present moment has a kind of power, a subtle ability to anchor a piece of the world, however small, against the relentless flow of time. The quantum Zeno effect is the ultimate demonstration that measurement is not a passive act of discovery, but an active force that molds the very substance of reality, holding it in a state of suspense for as long as we care to look. Our journey through the quantum tapestry arrives at a final, breathtaking possibility, a theory that places consciousness at the very heart of cosmic destiny. The final anthropic principle pushes beyond the idea that the universe is merely fit for life. It proposes that the emergence of conscious observers is not an accident, but the ultimate goal of the cosmos, a necessary ingredient for reality to fully realize itself. This is not just a universe fine-tuned for life, but one that requires life to complete its own existence. Think of the Big Bang as the first note of a grand symphony, a composition of unimaginable complexity. But a symphony requires an audience to be truly heard, to be transformed from mere vibration into experienced beauty. In this view, we are that audience. Our conscious observation is the final act of cosmic creation, the necessary event that gives a definitive past, present, and future to what was once only a fog of quantum potential. This ties together threads from many of our earlier theories. The participatory universe of John Wheeler finds its ultimate expression here, where our gaze does not just collapse a particle state, but helps solidify the entire historical narrative of the cosmos. The quantum Darwinian struggle for stable states reaches its peak in the human brain, a biological machine complex enough to host the consciousness that finally observes the winning reality. Even the holographic principle and emergent spacetime find a new role, as the stage and the screen upon which this conscious drama unfolds. This suggests that consciousness is not a fragile flame flickering in the void, but a fundamental feature of the universe, as intrinsic as space and time, or perhaps even more so. The laws of physics are not just right for life. They are right for the eventual emergence of minds that can look back and ask why. We are not just living in the universe, we are the universe becoming aware of itself, completing a circuit that began 14 billion years ago. The ultimate quantum reality may be that we are both the experiment and the experimenter, the dream and the dreamer. Our journey through these 30 theories reveals a cosmos stranger than we imagined, and perhaps stranger than we can imagine, with our own curious, questioning minds woven inextricably into its infinite, unfolding mystery. From the branching paths of many worlds to the ghostly consensus of the Copenhagen view, our journey across 30 quantum realities reveals a cosmos of stunning possibility. We have explored universes projected from two-dimensional boundaries, realities scripted from the first moment of time, and a cosmic stage that freezes solid under our gaze. We have considered the chance that we are living inside a simulation, that our consciousness is a quantum process, and that space itself is an emergent illusion. This wild diversity of thought is not a sign of confusion, but the vibrant sound of human curiosity pushing at the very edges of the known. Each theory, from the holographic principle to the cosmic superfluid, represents a different key, a unique attempt to unlock the same profound mystery. The true nature of reality remains one of science's greatest and most beautiful enigmas, a puzzle we are only beginning to piece together. These ideas are the cutting edge of that quest, the maps we are drawing for territories we have not yet seen. Now we turn this final question over to you. Of all these mind-bending theories, which one reshaped your understanding of existence? Share in the comments which concept blew your mind the most, and subscribe to join us as we continue our deep dives into the endless mysteries of the cosmos.